Welcome to the introduction to sets. A set is a well-defined collection of objects. According to the definition, all collections are not set. Only well-defined collection is set. Now it is common question. Which collections are well-defined? For instance, a collection of the 3 best dramas of Shakespeare is not well-defined because the term best are subjective. Although the number of elements in the collection is fixed at 3. The choice of dramas depends on an individual's opinion. Therefore, different people may select different dramas, and the collection may vary from one person to another. Another example. A collection of 5 tasty fruits is not well defined because tasty is subjective. However, the collection of vowels in the English alphabet is well defined because anyone can definitively agree that a, e, I, o, and u are its exact members. Sets can be represented in multiple ways. The tabular or roster form lists all elements explicitly separated by commas inside curly braces. The set builder form describes the common property suppose all elements, like x, such that x is an even natural number which is less than or equal to 8. A Venn diagram provides a visual representation, enclosing elements inside geometric boundaries. We will see later in this video. We can transform roster form to set builder format easily by identifying the mathematical pattern. We know the natural number are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So, there are 4 numbers less than 8 and even. In another example, this is quadratic equation. The solutions of this equation are 2 and 3. So the set has 2 elements only. Let's look at different types of sets. An empty set contains no elements. Like the set of natural numbers strictly between 1 and 2 has nothing in it. A finite set has a countable number of elements. Like days of the week, an infinite set is a set that is not a finite set. It is mentioned that infinite sets may be countable or uncountable, such as the set of natural numbers. Now, subsets are sets whose elements are entirely contained within another set. The universal set is a collection of all the objects related to a specific context. Let us go to visualize this. An empty set, written as the empty symbol or curly braces, contains no elements. For example, the set of natural numbers strictly between 1 and 2 has nothing in it, so it is an empty set. A finite set has a countable number of elements. For example, the set of days of the week has exactly 7 elements. An infinite set is a set that is not a finite set. Infinite sets may be countable or uncountable. The set of natural numbers is a classic example of an infinite set. Subsets are sets whose elements are entirely contained within another set. For example, if X contains 2 and 4, and Y contains 1, 2, 3, 4, and 5, then X is a subset of Y, since every element of X is also found in Y. The universal set is a collection of all the objects related to a specific context. For example, if U contains the numbers 1 through 10, both X and Y can be defined as subsets within that universal set. A set can also contain other sets as elements. Then we call it set of sets. A prime example is the power set. The power set of a set A is the collection of all subsets of A, including the empty set and the set A itself. If a set contains n elements, its power set will contain 2 raised to the power of n elements. We will describe it visually at Another time. The Cartesian product of two sets A and B, denoted across B, is the set of all ordered pairs where the first element belongs to A and the second belongs to B. Graphically, we can represent this on a coordinate grid, where elements of set A are mapped along the horizontal axis, and elements of set B are mapped along the vertical axis, forming clear grid intersections. Here A is the set contains 1, 2, 3 and set B contains 1, 2. So, Cartesian product of two sets A and B, denoted across B, contains 6 elements means 6 ordered pairs. These are 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2. Now we will see the another example. Here A is the set contains A, B, C and set B contains X, Y. So, Cartesian product of two sets across B contains also 6 elements means 6 ordered pairs. These are A, X, A, Y, B, X, B, Y, C, X, C, Y. Set operations allow us to combine or modify sets using geometric frames called Venn diagrams. Let us construct a universal set containing two overlapping sets, A and B, to visualize how operations behave. Each circle represents a set, and the region where they overlap represents elements shared by both. We will explore 3 key operations. Union, which combines all elements from both sets. Intersection, which keeps only the elements common to both. And difference, which keeps elements found in one set but not the other. As we go through each operation, watch how the shaded region changes to represent the result. The union of sets A and B, written as a union B, combines all elements from both collections. Visually, this corresponds to shading the complete area inside both circles entirely. Here, the shaded region is colored by orange. Now we will see an example. Here the set A contains 1, 5, 9 and the set B contains 5, 8, 11 if we collect all elements. Then we get 1, 5, 8, 9, 11 though the interaction part is different colored. But all are a union B. The intersection of sets A and B, written as A intersection B, captures only the elements shared in common. Graphically, this area is exclusively the central overlapping region where both sets cross paths. Here, the shaded region is look like red color. It is produced by overlapping colors effect. Let us look at the same example. Set A contains 1, 5, 9 and set B contains 5, 8, 11. The only element found in both sets is 5 into the green region. So, A intersection B gives us just the single element, 5. The difference of sets, written as A minus B, removes any elements belonging to B from set A. In our diagram, notice how only the unique left moon crescent of set A remains highlighted. Here, the shaded region is colored red. Using the same example, set A contains 1, 5, 9 and set B contains 5, 8, 11. We remove the element 5. Since it also belongs to B, what remains are the elements unique to A, giving us A minus B equals 1 and 9 into the green shaded region. Thanks for your patience and best wishes to you.